If you've used ChatGPT, Claude, or Gemini, you're already interacting with a large language model, or LLM. But what exactly is an LLM? How is it trained? Why does it behave the way it does? And most importantly, how can you use it more effectively in your work or learning? I've gone through hours of research and distilled the most important insights so you can understand LLMs at a fundamental level without needing a technical background. This video is the first in a practical explainer series for everyday users who want to improve their productivity and understanding of AI. Make sure to subscribe and turn on notifications so you can follow along and future-proof yourself. Stick around till the end. I'll explain key limitations and best practices that will help you get the most out of these powerful tools. What is an LLM? A large language model is essentially a giant mathematical function designed to predict the next word in a sequence of text. It's not a brain, not a database, and not a search engine. Unlike deterministic systems, some that always give the same answer, LLMs generate probabilistic outputs. That means for any given input, the model calculates multiple possible continuations, each with a probability. So when you ask the same question twice, you might get two slightly different responses. That's not randomness, that's probability at work. And it's part of what makes LLMs so powerful and occasionally unpredictable. How LLMs are trained. To understand why LLMs behave the way they do, we need to look under the hood at their training process. There are three major stages involved in training an LLM. Stage 1, pre-training. This is the foundation. The model is fed enormous amounts of text scraped from the internet. Think hundreds of billions of words. But before the model can read, all that text must be tokenized. Tokenization is the process of breaking text into small pieces called tokens. These could be whole words, parts of words, or even just letters. Think of tokens like IDs that represent parts of language. They're the building blocks the model uses to understand text. Each model has its own tokenizer, but the concept is the same. Text becomes structured data the machine can process. Once tokenized, the data is fed into a neural network, a massive mathematical structure with billions of parameters, or internal dials. Let's look at a simple example of what happens during training. The model sees the start of a sentence. The cat sat on it tries to guess the next word. Maybe it predicts table, but the correct answer was mat. So the model adjusts its internal dials to reduce the chance of making that same mistake again. This guess, compare, adjust loop happens billions or even trillions of times during training. Think of the neural network like a student learning to finish sentences. At first, it makes lots of mistakes, but over time it adjusts and improves. These adjustments happen inside the model's parameters. Think of them as tiny dials that shape its behavior. Each time the model updates, its parameters become better tuned to the patterns of human language, grammar, tone, sentence structure, even factual associations. By the end of pre-training, all of this learned knowledge is compressed into the parameters. But it's important to understand, the model does not memorize the documents it trained on. It stores abstract patterns, not exact facts or files. This pre-trained system is called the base model. It's excellent at mimicking language, but it isn't yet an assistant. It doesn't understand your intent, and it doesn't know how to help. At this stage, it's simply auto-completing text statistically based on what it has learned. One more key concept before we move on, the context window. Even though the model has been trained on a vast amount of data, during actual use, it can only see a limited portion of text at any one time. This limit is called the context window, and it works like the model's short-term memory. For GPT-4, that window is typically 8,192 tokens. Some versions go up to 32,000 or even 128,000 tokens. Now, a token isn't the same as a word. It might be a whole word, part of a word, or even punctuation. Roughly speaking, 8,000 tokens is about 5 to 6 pages of text. So far, the model has learned how language works, and it holds that general knowledge in its parameters. It can also process short-term input through the context window, which is essential during live interactions. But there's still something missing. At this point, the model still doesn't know how to be helpful. It doesn't understand how to answer questions or respond like an assistant. That's where the next phase comes in. Stage 2, Supervised Fine-Tuning, SFT. This stage is essential to make the model actually useful, whether as a chatbot, an assistant, or a domain-specific tool. In this phase, the base model is further trained on human-labeled conversations. Examples of users asking questions and assistants giving helpful, structured replies. These examples teach the model not just language, but how to follow instructions, how to be useful, and how to hold a conversation. For example, it learns that when someone asks, "Can you explain photosynthesis?" the correct response isn't just random facts. It's a clear, well-organized explanation. This is when the model starts to act more like an assistant. But make no mistake, It's still imitating human behavior, not truly reasoning on its own. At this point, the model is called an SFT model, short for Supervised Fine-Tuned. But imitation alone has its limits. To help the model improve and sometimes even outperform the examples it was given, we need one final phase of training. Stage 3, reinforcement learning. In this final stage, the model is trained not just to imitate, but to optimize. It does this by repeatedly generating answers to the same prompt and receiving feedback on which responses are better, based on a chosen reward signal. Here's how it works. The model is given a prompt. It generates multiple possible responses. A separate system, either a human or another model, ranks or scores the outputs. The model is updated to make better answers more likely in the future. Over time, the model learns to prioritize usefulness, clarity, and safety, not just repetition. This stage is where we start to see thinking-like behavior emerge. The model improves its ability to reason, evaluate, and solve problems, not because it understands, but because it's been trained to perform better under feedback. This area is still nascent and experimental, with no single best method established yet. Different companies are exploring a variety of approaches. One example is DeepSeek R1, where models are trained not just to answer questions, but to approach problems cognitively. If you're interested in learning more, check out my earlier video on DeepSeek by clicking the link in the top left. Reinforcement learning is how we push LLMs from being just useful assistants to becoming powerful problem solvers. Cognitive implications and limitations of LLMs. 1. Memory. What the model knows and remembers. LLMs don't remember the way humans do. They operate with two distinct memory systems. Pre-trained parameters. All the general knowledge the model learns during training gets stored in its parameters. Think of this like fuzzy long-term memory. It remembers patterns, styles, and facts in an abstract way, but not specific documents or details. Context window equals short-term, precise memory. The context window is the text the model can see during a conversation. It's limited. For GPT-4, this usually ranges from 8K to 32K tokens. Once older parts fall outside this window, the model literally loses access to them. Parameters are like something you vaguely remember reading last year. Context window is like something you just read 10 seconds ago. Vivid, but temporary. Everyday implications. The model can't reliably remember things you said earlier in a long chat. It won't recall facts just because it saw them during training. What to do instead? Restate key information in each prompt. Paste relevant content directly into the input. Use models with extended context windows for long documents. For long tasks, break content into shorter chunks. To better illustrate this, let's walk through an example. Imagine you're working with a 60-page company report. You paste the entire thing into the model and then ask, "Can you tell me what the CEO said about sustainability?" Now here's what often happens. The model may give you a generic or vague response. That's because it has to search blindly across all 60 pages, and even though the content technically fits within the context window, the model might still miss the key quote. A better approach would be to guide the model more precisely. Try saying something like, "In the report I pasted, the CEO's comments on sustainability are on page 58. Can you extract and summarize just that section?" With this clearer and more specific prompt, the model knows exactly where to focus, and you're much more likely to get an accurate, useful answer. 2. Reasoning. How the model thinks or doesn't. LLMs simulate reasoning by predicting statistically likely continuations. This isn't logic-based reasoning, it's pattern completion. Probabilistic outputs. The model doesn't choose one right answer. It generates a distribution of plausible continuations. That's why results can vary even with the same input. Not great at math or logic. LLMs struggle with arithmetic, logic, and step-by-step calculations because these require systematic rules, not statistical guessing. Spelling and syntax issues. Because models work with tokens, not letters, they may misspell, misformat, or confuse unusual names or rare words. Everyday implications. Don't rely on LLMs for mental math, counting, or financial modeling. Avoid relying LLMs for tasks that need strict logic or precision. What to do? Instead, use tools like Python by adding use code in your prompt for math or data tasks. For logic-heavy work, guide the model with step-by-step reasoning prompts and using thinking models that have been trained with reinforcement learning. Let's look at a quick example. If we ask the model to calculate a complex problem like the one shown on screen, let's see what ChatGPT 4.0 returns. Then we'll verify the answer using Python code by adding use code to the prompt. Both methods give similar answers. Now let's do the same with Gemini and Grok. Without using code, both Gemini and Grok gave incorrect answers. However, when asked to calculate using code, both provided the correct result. So for complex mathematical calculations, it's always better to use code instead of relying on the model's internal mental math. 3. Knowledge. What the model is and isn't. Trained on what the model knows is completely defined by its training data, which includes books, websites, forums, and code up to a certain point in time. No real-time updates. LLMs don't have access to new events or recent research unless it's specifically added through plugins or custom tools. Niche and rare topics are fuzzy. If a topic wasn't widely discussed online, the model may hallucinate, generalize, or just get it wrong. Not a fact database LLMs don't store verified facts. They generate plausible-sounding responses based on patterns, which sometimes means hallucinated names, dates, or citations. Everyday implications. Avoid using LLMs as your only source for niche, obscure, or emerging info. Don't expect accurate citations or real-time knowledge. What to do? Instead, provide source material directly in your prompt if accuracy matters. Don't treat a single model's answer as definitive. Ask the same prompt across multiple LLMs and compare results. For real-time updates, try Grok. It's integrated with live data from X. Always verify generated facts and citations or claims manually. Summary. What you've learned about LLMs. Let's wrap up with the key insights. LLMs are probabilistic word predictors. Not brains, not databases, and not search engines. They generate responses by calculating likely continuations of your input based on learned patterns from training data. They are trained in 3 stages. Pre-training, where the model learns how language works by guessing the next word in billions of sentences. Supervised fine-tuning, where it learns to respond like a helpful assistant using curated examples of human conversations. Reinforcement learning, where it improves by receiving feedback on which responses are more helpful, clear, or safe. The model's knowledge is stored in parameters, billions of internal dials that encode fuzzy patterns about language, facts, and structure. These parameters don't hold exact documents or memories, just statistical associations learned from training. The context window acts as the model's short-term memory. It only includes the prompt, recent conversation, and system instructions. And once older content falls outside that window, the model loses access to it completely. Now that you've got a solid grasp of how LLMs work, here's where the real magic begins. When you learn how to talk to them better. Let's look at a quick example. Imagine asking the model, "Tell me about marketing." It's broad, and you'll probably get a generic answer. Not very helpful. Now try this instead. Explain 3 effective digital marketing strategies for a small e-commerce business, with 1 example for each. Same topic, completely different outcome. This time, you've given the model direction, context, and a clear ask. And the result? A response that's focused, relevant, and actually useful. That's the real secret of prompting. It's not just what you ask, it's how you ask it. And that's exactly what we'll explore next. The next video in this series is Prompt Engineering 101, where I'll show you how to craft better prompts, avoid common pitfalls, and unlock the full potential of AI in your everyday work. So make sure to subscribe, hit that notification bell, and follow along. This is how you future-proof your AI skills, 1 smart prompt at a time.